Good afternoon again. We're approaching the last bit of work and energy and power. Second before last bit. There's also power at the end. Anyway, the big thing of this chapter is this. It's the conservation of energy. The question now is, what does that mean? Well, qualitatively, all the energy that an object has at any given time, it will always have. All the mechanical energy is what it will always have. The mechanical energy is the sum of the kinetic energy and the potential energies. But an object that has a combination of kinetic energy, gravitational potential, and spring potential energy has mechanical energy. Often it will have kinetic energy and one of the two potential energies. It probably never will have just kinetic energy and no potential energy. At least not if we want to consider the conservation of energy. The conservation of energy is written, that's it, where E is the mechanical energy. We can write it in a couple of different ways, and how you write it just depends on what's the purpose of it. But the conservation of energy is more often written as delta K plus delta U is equal to 0. And that is the big thing. But, there's always a but. It is the big thing if your system is isolated and closed. If no external influence act on the system, and if no friction is there. If there is friction, for example, consider the eraser here. I don't know if you can see it, hopefully you can see it. The eraser, I will give it a flick. As soon as it leaves on my finger, it's not under the influence of my finger anymore. It only has one, its displacement is horizontal, that it only has one force acting horizontally, that's the friction force. It slows down. It lost energy. It stayed at the same height. Its change in potential energy was 0, but its kinetic energy went down to 0. What happened with the friction force? Well, the friction force is an external force to the system. It is a non-conservative force. So it seems to violate the conservation of energy. But that's because we ignore what the friction force does. It creates a non-conservative work that takes kinetic energy and transforms it into thermal energy in the atmosphere. As soon as you consider the atmosphere and the eraser, you have back conservation of energy. However, we won't delve this far. For our purposes, the system consisted of the eraser and the table with friction. So conservation of energy, if that happens, if we do have either of those, this transforms into, or this generalizes into the work-energy theorem, which says that the change in kinetic energy plus the change in the potential energies, gravitational and spring, is equal to the sum of the works done by non-conservative forces. And those two are external forces and friction forces. You can think of the conservation of energy here as a specific case of the work-energy theorem. So here's my advice for whenever you solve a conservation of energy or a work-energy problem, is you start with writing down the work-energy theorem, and then you ask yourself, is there an external force? If yes, you keep this form. Is there friction? If yes, you keep this form. If you have no external force and no friction, this goes down to 0, and you have the special case of conservation of energy. Often in problems, if you have friction or an external force, the problem will state that you start and end at the same speed, so you can remove the change in kinetic energy. Or the problem will state that you stay at the same height, so you can remove the gravitational potential energy. it might not say that, and you might need to consider everything. For example, look at the skier problem in between the two hills. I cannot remember the number of that problem, but it's one of the videos that I have online. Part of it necessitates the work energy theorem, but it's a case where you actually have no change in kinetic energy because you start the problem at 0 speed, you finish the problem at 0 speed. And that's it for the work energy. This is the starting point. Look up if you have external force or friction, and then you can have the conservation of energy if those two conditions are satisfied. Let's see you in the next one.